In this video, practical control for VTOL UAVs to avoid non-cooperative moving obstacles will be introduced. Airspace is utilized today by far lesser aircraft than it can accommodate, especially low-altitude airspace. There are more and more applications for UAVs in low-altitude airspace. One of the chief concerns regarding UAVs is obstacle avoidance problem. In the obstacle avoidance problem, the obstacle can be divided into two categories. Cooperative obstacle and the UAV can make avoidance with each other by slowing speed or changing their directions. Obviously, compared with cooperative obstacle, the non-cooperative obstacle is more difficult to deal with. To formulate the non-cooperative obstacle avoidance problem, a UAV model is introduced first, including the UAV control model and the speed limit. Then, a filtered position model is defined as follows by considering the velocity. Two types of areas, namely safety area and avoidance area, are defined. Finally, an obstacle model is proposed containing the obstacle radius, the filtered position of the obstacle and the speed limit. For the UAV and obstacle, we have the following assumptions. In Assumption 1, for easy analysis, the information of obstacle is known, where the velocity of obstacle is constant. In Assumption 2, the UAV should not conflict with the obstacle initially. In Assumption 3, the goal waypoint should be static. Moreover, it should keep a safety distance from the obstacle if the obstacle is static. The objective is to design the velocity input for the UAV model to guide it flying until it arrives at the goal waypoint, meanwhile avoiding colliding the obstacle. The idea of the proposed method is similar to that of the artificial potential field method. For the UAV only is the corresponding waypoint assigned attractive potential, while the obstacles are assigned repulsive potentials. A UAV in the field will be attracted to the waypoint while being repelled by the obstacles. The proposed controller lies on the following features. First, the maximum velocity command in the proposed distributed controller is confined according to the requirement of semi-autonomous autopilots. The velocity command will not be dominated by the term of approaching to waypoints in the case of the UAV is very close to the obstacle. This can avoid a danger. Second, the physical meaning of controller is introduced. The controller can be written as a proportional controller. The control command is generated by the combined force of attraction and repulsion. Third, the stability analysis is divided into two parts. When the obstacle is static, the equilibrium point is only lying on C half line. Then, the UAV can only be stable in one-dimensional space, whose measure is 0 on a 2D space. When the obstacle is moving, Lemma 3 shows that the relationship between the obstacle and the UAV will tend to the case C. The following analysis is similar to the situation that the obstacle is static. The results above can be extended to multiple obstacles as well. For the multiple non-parallel moving obstacles, Assumption 2 is replaced with a new one. After enough time, non-parallel obstacles must separate far enough with each other. In this case, only one obstacle at most needs to be considered for the UAV after enough time because the others are out of its avoidance area. The multiple moving obstacles problem can be degraded to the one moving obstacle avoidance control problem. For the multiple parallel moving obstacles with the same velocity, Assumption 2 is replaced with a new one. The obstacles can be taken as one combined obstacle with appropriate center position, velocity and radius. Then, the problem can be degraded to the one moving obstacle avoidance control problem. The proposed method can still work. During the simulation, 3 different scenarios are designed according to the situations above. In Scenario 1, one static UAV makes avoidance with one moving non-cooperative obstacle is considered. The distance between the UAV and the obstacle is shown in figure. The estimated filtered position distance is more than safety distance during the experiment. In Scenario 2, one UAV makes avoidance with 3 moving non-cooperative obstacles is considered. The radius and velocity of each obstacle is different from others. Further, the distance between the UAV and each obstacle is shown in figure. Similarly, the estimated filtered position distance between the UAV and each obstacle is more than its safety distance during the experiment. In Scenario 3, one UAV makes avoidance with 5 parallel moving obstacles with the same velocity is considered. The radius of each obstacle is different from others. These obstacles are taken as one combined obstacle. Further, the minimum distance among the UAV and obstacles and the estimated filtered position distance between the UAV and the combined obstacle are shown in figure. Similar to the simulation, 2 different experiments are designed to show the effectiveness of the proposed method. In Scenario 1, one UAV makes avoidance with multiple parallel moving obstacles with different directions as shown. Finally, the UAV can complete its route, keeping a safe distance from moving obstacles without confliction. In Scenario 2, one UAV makes avoidance with 3 parallel moving obstacles with the same velocity is shown. These parallel obstacles arrange in a V shape. Finally, the UAV can complete its route and avoid getting stuck, keeping a safe distance from moving obstacles without confliction. That's all. Thank you for your watching.